Hello everybody. Today's lesson is working stress method. During the design of RCC structure, there are two methods. One is working stress method, another is limit state method. Okay. So throughout this video, I will discuss about this working stress method. So at the very first, what is working stress method? Well, at the very beginning, I will not say anything related to this working stress method. Okay. Let's say this is the starting of this video and this is the ending of this video. So throughout this length or throughout this journey, there are some, let's say there are some park, there are some greeneries, there are some river, there are some lake, and you have to make this journey complete to reach here. And this whole journey is working stress method. Okay. So let's start our journey. At the very beginning, this is the beam, and if you apply any load, okay, so of course due to this load there will be some bending moment, okay. And if you take any part of this beam, let's say you are taking this part is under the action of bending moment, let's say M, okay. So this is the actual load. Let's say this is the weight of your body, okay. So let's say the weight of your body is P, and if the length of the beam is L, in that case what is the moment? Of course this is M is equal to P L by 4, okay. Now if I ask you to design this beam for moment M, that is PL by 4, what you have to do? You have to simply use this value, okay. You are not supposed to increase this value by multiplying some factor. So this moment is based on the working load, okay. So here is the keyword, that is working load. So keep it in mind, this is working load, okay. Now in the lesson of strength of material, you have already learned that due to any moment, if this is the section, let's assume a rectangular cross section, and this is under the action of this bending moment, so at any point your stress will be generated, that can be expressed by this formula, that is sigma is equal to my by I, okay. And this stress is caused by this working load, okay. That's why this stress is known as working stress, okay. So till now nothing is new to you, everything is related to your strength of material lesson, and you have learned what is working stress. Of course, to make this cross section you have to use any material. Let's say this is steel or wood, or let's say this is aluminium, or let's say this is concrete, whatever it is. It has some yield stress, that is sigma y, and this yield stress is the limit after which it cannot take any further load, okay. Now for design purpose we cannot use this value as the ultimate value, because let's say your body is of weight W, and for that the bending moment is your WL by 4, and for that stress is something which is function of W, and you have designed this beam based on the yield stress, okay. This sigma is equal to sigma y. Now suppose in one of your hand someone put some weight, obviously this W becomes W plus delta W, and this stress will become sigma plus delta sigma, which is greater than the yield stress, so this beam is going to be collapsed. That's why we restrict this stress value below the yield value, we keep some margin, okay. Let's say this is the sigma y, and we keep our stress up to here. This is sigma. So this is the range where we can increase our sigma value in case of emergency. Okay, so now it is clear to you what is working load and what is working stress. And in working stress method, what we do, we don't increase the load, we keep it the same, but we reduce the stress, okay, which is less than the yield stress. And this stress is expressed by your, let's say, sigma y by some factor of safety. This is sigma. Okay, now again go move further. Let's say this is the beam which you need to design, and here there are some load, and due to this load at any section there is a moment. Let's say this is M, and consider the cross section. Let's say this is a rectangular cross section. Okay, so if this is the rectangular cross section, you know that the assumption in our bending theory of bending is that plane section remain plane. You have already learned what is the meaning of this plane section remain plane in the lesson of strength of material. Okay, the meaning of this is, if this is the beam, let's say this is the beam and this is the support, we have applied load here, and after application of load it will bend like this. Okay, plane section remain plane means this face which is plane remain plane each and everywhere. This is maintained, and practically this is also true. That means this assumption has been made based on numerous practical experiment. Simply before application of load, you make some marking with chalk, okay, at the face of your beam, that is straight line, and after bending we will observe that the line, this chalk, is like this, it is not like this. Okay, this is not the picture. So this is the meaning of plane section remain plane. So this assumption is also valid for working stress method. And you know from theory of bending, the strain is expressed by epsilon, that is your y by r, where your r is radius of curvature and y is the distance from this neutral axis. So if we draw this strain profile, it will look like this. Okay, now instead of using this steel or aluminum section, let's use some reinforced section. What is reinforced section or singly reinforced section? That is, at this top there are concrete, and at the bottom, yes, there are concrete, and also there are some steel reinforcement like this. But we neglect this concrete, we neglect this whole concrete which are in tension. Okay, so now the section looks like something this. First, at the top, yes, this is the concrete portion. Okay, this is the neutral axis, and at the bottom there are some steel. Okay, in between this, our assumption is it is void. This is void. So the strain profile looks like this. This is the strain in concrete, but in steel the strain is only acting here. Okay, these are your compressive strain and expressed by epsilon, that is y by r, and here this is also epsilon, that is y dashed by r. Based on the value of y, this changes. Okay, now let's say this now let's say the fiber, this fiber, okay, or the furthest fiber in concrete is at a distance of y, and the furthest fiber of this steel is also at a distance of y. Okay, now when you are applying your bending moment, what will happen? In actual case, it is not void. This void is not actually void. What is there? Yes, there are some concrete. Okay, we are neglecting this concrete, but in real cases, yes, there are some concrete, and in between this concrete or within this concrete there are steel reinforcement like this. Okay, so from this strain diagram, if we again draw it, it will look like this. At this point the concrete is also strained, and as well as the steel is also strained, and the strain is same for both cases. So we can write the strain in steel is equal to strain in concrete. Okay, from Hooke's law, you know that stress is equal to modulus of elasticity times strain. So the strain in steel is stress in steel divided by your modulus of elasticity of steel, and strain in concrete is equal to stress in concrete divided by modulus of elasticity of concrete, which can be further reduced to that sigma st is, this is sigma st. So sigma st is equal to your sigma concrete times E of st divided by E of concrete, and this special term is expressed by m. So what is m? Simply m times your sigma concrete, where m is your modulus of elasticity of steel divided by modulus of elasticity of concrete. Again, with respect to this modular ratio, the working stress method is saying that our assumption of modular ratio is given by 280 divided by 3 sigma CBC. This is given by IS456. This is another assumption of working stress method. Okay, so let's dive into modular ratio. What is sigma CBC? At the very beginning, I have already discussed that the stress we are taking of any material, we limit this by some factor of safety for emergency purposes. Okay, and here sigma CBC is sigma, or rather it is FCK. You know what is FCK? This is the cubical crushing strength. Okay, so cube crushing strength is FCK. This is divided by your factor of safety, and here factor of safety is equal to 3. Okay, so sigma CBC becomes 1/3 of cube crushing strength. That is the allowable stress in concrete when the concrete is under the action of bending. Clear? So sigma CBC is the allowable compressive stress under bending. Okay, so what is the meaning of CBC? Compressive strength under compression caused by bending moment. Okay, and now let's see whether this modular of ratio, which is given by IS456, is actually correct or not, or how this formula came. Okay, so theoretically modular ratio is modulus of elasticity of steel divided by modulus of elasticity of concrete. Okay, and m is EST, that is 2 into 10 to the power 5 divided by what is modulus of elasticity for concrete. While this is your E for concrete, short term elasticity is 5000 square root of FCK. Okay, so this is 5000 Here this is 5000 times square root of FCK. Okay, and sigma CBC is nothing but 3 times sigma CBC is FCK. Okay, because sigma CBC or allowable compressive stress under bending of concrete is taken as 1/3 of FCK. So replace this, simply 2 into 10 to the power 5 divided by 5000 times square root of FCK, that is coming as 3 times sigma CBC, or it is coming as your 200,000 divided by 5000 times square root of 3 times square root of sigma CBC. Okay, let's calculate it. 30 cancel 30, now 5, this is coming as 40, so 40 divided by square root of 3, which is coming as 40 divided by square root of 3 into square root of sigma CBC. But modular ratio in code is given as M is equal to 280, or we can write it by your 280 divided by 3 sigma CBC, and here let's make this 3, so 40 times square root of 3 divided by square root of 3 into square root of 3 into square root of sigma CBC. So it is coming as 40 into square root of 3, that is equal to almost 70. So 70 divided by, this is 3 into root over sigma CBC, and here let's make it 280, that is 70 into 4 divided by 3 into square root of sigma CBC into square root of sigma CBC. Okay, so compared to the actual or theoretical modular ratio, here the modular ratio which is given in code is given as M theoretical, let's say this is theoretical, times 4 divided by square root of sigma CBC. Okay, where sigma CBC is the allowable compressive stress when concrete is under bending, and you know that this is sigma CBC is 1/3 of FCK, and when FCK or concrete is of 50 grade, that is M50, in that case sigma CBC is given as 16 in code. Now apply it, so square root of 16 is 4 and cancel 4, this theoretical, now modular ratio becomes equal with your theoretical value. Okay, now you may ask, why for other grade your M as per code is given more than the theoretical with this factor 4 divided by sigma CBC, square root of sigma CBC? Well, here in our calculation we have taken the modulus of elasticity of concrete as E equal to 5000 times square root of FCK. You know, this is short term modulus of elasticity. Okay, but in code this modular ratio has taken into consideration your long term effect like creep. That's why it has been increased by this factor. Okay, if you use actual E, that is E is equal to E short term divided by 1 plus theta, where theta is creep coefficient, you will get this exact value. So till now if you thought that, well, I think this value was from empirical formula, you are completely wrong. Now let's recap. Okay, so in this journey you are almost here, you have reached almost here. Okay, and let's recap what are the assumptions which I have made in working stress method. First is we have to consider working load. Second is we have to consider working stress, and third one is we have to consider some factor of safety in stress, in allowable stress. Well, third one is plane section remain plane. Okay, fourth one is we have taken the stress and strain diagram linear, or we can say that our assumption is in all this discussion Hooke's law is valid. And when the stress is comparatively low, only in that case Hooke's law valid. That's why we have controlled our stress by application of a factor of safety, or you can say we have taken only 1/3 of maximum stress. Okay, and then the modular ratio. The modular ratio as per code is this one, and you have got the proof from where this has came. Now let's finish the rest of journey, and now we will learn how to find the moment of resistance of any section. Okay, before finding moment of resistance you need to learn one more thing, that is, if this is the reinforced section, we have considered a neutral axis. Okay, but till now we have not calculated this depth of neutral axis, or how to find this depth or x. Okay, so what is the strain diagram? It is linear and it is something like this. Okay, this is the strain in concrete and this is the strain in steel. Okay, and this angle theta is same for both cases. So for concrete we can write that the tan theta is the strain in concrete divided by this height or depth x, and let's say the depth of reinforcement from the top fiber is d. Okay, so what is this depth? Simply d minus x. So tan theta for steel is coming as strain in steel divided by d minus x, and both cases the tan theta is same, so we can write the strain in concrete by x is equal to strain in steel divided by d minus x, or again apply Hooke's law. So stress is equal to E times strain, or strain is equal to sigma divided by modulus of elasticity. So here it is coming as sigma CBC divided by EC, or concrete. Okay, and x remain. Here for steel this is coming as sigma ST. Let's say sigma ST is the allowable stress in steel, and divided by EST. Okay, d minus x remain, and from this equation we can calculate d minus x by x is equal to coming as sigma ST divided by EST times sigma CBC divided by E of concrete, which gives you d by x minus 1 is equal to sigma ST divided by, this is nothing but modular ratio, that is m times sigma CBC. Okay, or again as per code m is given as 280 divided by 3 times sigma CBC, so replace it, you are getting sigma ST divided by 280 times sigma CBC divided by 3 sigma CBC. Cancel them and you are getting d minus x minus 1 is equal to d by x minus 1 is your 3 times sigma ST divided by 280. okay, or we can write that x is equal to 3 sigma st by 280 plus 1, okay, and this is the denominator with numerator as d, okay. So now you can find this depth of neutral axis, and it is completely a function, x is a function of your strength of steel, not concrete. Now this is the section, this is the neutral axis. You have already find out the depth x, okay, this is the depth of neutral axis, and here is the reinforcement, okay. What is the strain diagram? It is like this. And what is the stress diagram? Of course, sigma proportional to strain, so the stress strain diagram is linear. That was also our assumption because Hooke's law valid here. So this is the stress diagram, and the allowable stress in concrete is sigma CBC. In steel, this is sigma ST, and we don't consider this concrete, so this is void. So in stress diagram we can show like this. This is the only stress acting in steel, and for concrete this is the compressive stress acting throughout this depth up to neutral axis, okay. So this is the triangular distribution. We can say that the resultant stress or total stress is, if width is b and depth is d, this is the depth up to reinforcement. So what is the total area of this triangular section? Well, this is half times sigma CBC times this is x, which is known to you, x into width, because in 3D if you look, the stress is distributed like this, okay. So this is multiplied with b. This is the total area of compressive force, okay. So this is C, and it is acting at a depth of xy3. So here this is the resultant compressive stress or compressive force. Well, this is the stress in. Now let's say you have total area of steel as AST, and allowable stress in steel is sigma st. So what is the total tensile force acting in reinforcement? That is sigma st times AST, okay, and T is given by sigma st times AST, okay. So now again draw this diagram. If this is the section, this is the neutral axis, here is the compressive force, here is your tensile force, and the distance in between them is total depth from here to here is d, and this is acting at a distance of x by 3. So this is coming as d minus x by 3, okay. And here from equilibrium, total compressive force is equal to your tensile force, and this condition is known as balanced condition. Now if you look here, this is the neutral axis and this is compressive force, this is tensile force, okay, and here C is equal to T, so they are acting like a couple, and the lever arm is your d minus x by 3. So what is the moment? Of course the moment is given by either C or T, as both of them are equal, times the lever arm, that is d minus x by 3. D is known to you, x you have calculated from this formula. So now the moment of resistance of the section is given as either compressive force or tensile force. Compressive force is this one, okay, that is sigma CBC times sigma CBC times x times b by 2 into lever arm, that is d minus x by 3, or you can use the tensile force, that is sigma st into ast into lever arm, that is same, d minus x by 3. Okay, so in this video you have reached almost here in this point. Okay, the remaining one is this distance, and here I will discuss your over reinforced section and under reinforced section in the next video.